Good morning, everybody. Good afternoon.
This is the IEEE Computer Society Distinguished Lecturer Webinar Series brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors around the world who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Hello to everyone joining us around the world. It's a beautiful day in Washington, D.C. area, and I'm enjoying it safely behind a plate glass window. I hope all of you are keeping safe and healthy. Welcome to our Distinguished Lecturer Webinar Series. Before we go any further, my name is Kerry Cosby, and I'm the Chapters Manager here at the IEEE Computer Society. I oversee our 500 professional and student chapters around the world and manage our Distinguished Visitors Program. Before we get started, I'd like to get a couple of housekeeping tasks out of the way. You can ask your questions in the Q&A panel. Dr. McMillan will answer as many questions as he can following the presentation. The webinar is being recorded, and the slides and recording will be made available within a few days after the webinar. Today's lecture will cover an interpretation of formal information flow properties and interference within the context of a cyber-physical system, blending both physical and cyber information flow properties across multiple security domains. Today's speaker is Dr. Bruce McMillan, Professor and Interim Chair of Computer Science at the Missouri University of Science and Technology. He's also the Director of the Center for Information Assurance and Co-Director of the Center for Smart Living at the Missouri University of Science and Technology. He leads and participates in interdisciplinary teams in formal methods for fault tolerance and security in distributed embedded systems with an eye towards critical infrastructure protection. His current work focuses on protection for advanced power grid control. Dr. McMillan, thank you very much for presenting to us today. I'd like to hand the floor over to you.
Thank you, Kerry. And again, good morning, good afternoon, good evening around the world. Thanks for joining today. So again, my name is McMillan. I'm with the Missouri University of Science and Technology. And I just want to introduce that I'm not in Washington, D.C. I'm actually at my home location here in the state of Missouri. Where am I? Okay, so you know where you are. So let's try to figure out where I am. Aha, United States. And literally right in the center of the United States. And if you're familiar with the U.S., or maybe not, Missouri, University of Missouri S&T, or just S&T, because it gets to be quite a mouthful, is in a town called Rolla. We're near St. Louis, the St. Louis Arch. We have our own primitive computer, which is a half-scale model of Stonehenge cut by our water jet technology people. And we are really a very large STEM school, science, technology, engineering, and mathematics. We have 7,500 students across 17 engineering programs. I tell you that because of the topic that I'm really talking about, which is cyber-physical systems. And this term has been popularized, I guess, within the last 20 years. And you can see the definition here. The way to think about it is that it is some sort of physical device, some sort of physical system with computing deeply embedded in it. Some examples might be a water treatment plant, where you've got physical pumps and filters controlled by programmable logical controllers, the electric smart grid, which Kerry talked about a little bit in the introduction. It's not just power flowing the way power wants to flow, but power being directed under cyber control. Advanced manufacturing and autonomous vehicle is another example, where you've got artificial intelligence controlling control systems, controlling the physical systems, airspace management, aircraft moving around, and essentially not running into each other, but also taking off and landing under autonomous cyber control. To be able to do this requires that we really have a deep understanding of how computation relates through the physical system into control, how communications relates to different parts of the physical system, and back to computation. So let me give you an example of something, maybe a transition here as we transition towards more cyber-physical systems. So that's an abstracted picture of a power distribution system that we're all pretty much familiar with. In the background there, in the gray, are the source of electric power. You've got coal, nuclear, maybe wind. You can even put hydro in there. And the power comes down to your house, to your neighborhood. Well, cyber-physical systems starts to look at this a little bit differently. And you see the big sign on the front that says governance. And that's a leaderboard system that might be used within a neighborhood to be able to talk about collectively your usage of electric power and how do you more efficiently use electric power. So we change the world from just receiving electric power produced by some other type of producer into a community type of discussion. Well, how do you actually do a community governance? How do you do a community shared governance? It's actually a localized management of your energy resources instead of a distributed or instead of a remote type of lack of management or management by somebody else. And the power can be locally sourced. It doesn't have to be brought from somewhere else. What do you mean by locally sourced power? Well, you can have your own wind turbine on top of your house. You can have your own solar cells on top of your house, and you can buy and sell power from your neighbors. So it's a very, very different type of concept. And to be able to do this requires that you have locally embedded computation working with the underlying electric power system. We also have to talk a little bit about security at this exact point. This is definitely going to be a security talk and information flow within security. Let's think about security domains. What does it mean for such a system to be secure? We usually think about security in terms of cryptography. That's what first comes to mind, or high security, low security protection domains. Such a concept is very difficult to do in such an environment. And we also have to preserve privacy, because think about a leaderboard system. Do you really want your neighbor looking inside your house? Well, no, but you'd like to participate in maybe a shared type of energy management system. So these are challenges now that you have when you have a cyber-physical system and you put people in it. So this is probably a traditional picture, but let me redraw it here. Let me think about what it should look like. It's the same houses, but now I've got security domains which reflect a lot more of how the physical system really operates. Those three houses, A, B, and C, think of the old adage, one's home is their castle. So it's okay to see the outside of the house, but you don't really want to see what's inside the house. That's privacy, but you still want to be able to interact with the outside world. So that's this other label called support, the grayish interaction here. Essentially the power lines that run between the house, or perhaps, we'll leave it at that, the power lines that run between the house. But then how's the whole thing managed? Well, this governance here has to be able to manage the system, to be able to direct power back and forth. But yet, the governance system should not be able to see inside the house, but it can see how the houses interact. So we have a very, very different kind of novel way of looking at security here. So let that sink in for just a bit, and then I'm going to show you something odd. So here's a graph in the middle of the first part of a presentation, which is a very peculiar thing to see. But what you're seeing is on the lower axis there is time of day. So we have midnight, and we're running along to the right, and all of a sudden we get these spikes. And then what's on the left axis is the amount of power usage. And you can see the colors here are appliances. The toaster comes on. You use the bathroom light fixture. The water heater comes on. So these spikes show that essentially the usage inside the house. Now, the reason that I'm showing this is, remember in the previous slide we had the governance? You could simply see the outside of the house. Where did this graph come from? This graph was obtained by simply sitting outside of the house, monitoring the power fluctuations in the usage. No internal instrumentation. We call this data exhaust. Simply by the activity of the electric power system, all of a sudden we begin to generate data and we begin to generate information that flows out of the system. And we do not anticipate that at all. So I'm setting up a problem here which talks about really the complexity of how one deals with security and privacy in a cyber-physical system. So let's return back to our picture here. What do? Management and governance. What do standards organizations say about this? That picture that I just showed was from a NIST report that I was involved with, 7628, a number of years ago. And NIST really took the view at that time that privacy was something that we might worry about with smart meters, but in reality, we're really worried about maybe people buying and selling somebody's information to do advertising, kind of not really looking at the privacy issue directly on. Well, what else? How do we manage this thing? What about cloud? Everybody talks about cloud. Well, one aspect of cloud is kind of interesting. NERC is an acronym for North American Electric Reliability Corporation, and CIP is Critical Infrastructure Protection. And NERC CIP standards say you really should not divulge what kind of control settings you're doing in an electric power system. But wait, that graph I just showed, that's exactly what it was doing. It's not so great. Also, the problem with cloud might be that you have some sort of remote management of the system, but if you look at that picture there, everything's happening locally. So I'll turn next to another concept called fog. I don't know if you've heard of fog computing or not. There's a bit of a joke, which I'll talk about in the next slide, of where the term comes from. But in reality, it's an Internet of Things. And cyber-physical systems are Internet of Things. In this case, for energy management, it's locally managed and locally produced and locally protected. And this is what we want to try to go to. Now I'm going to diverge for just a second here and do some definitions. Okay, cloud. We've all heard about the cloud. Put it in the cloud. What's a cloud? That's the cloud. There is no cloud. It's just somebody else's computer. This is the cloud. So let's get the notion the cloud is some sort of magical thing out of our head. All right, so it's computers somewhere else. Fine, I can accept that. So what's a fog? Now comes the funny part. What's the meaning of fog? Well, what is a fog? What is fog? Fog is a cloud. It's a cloud on the ground. Get it? So you're putting the computational intelligence from the cloud right next to the activities that are occurring. And the example that I have here is power usage. Let's see, I've got some extra spaces here. Mist. Mist is at the edge of a fog, right? You can really get carried away with this. Well, what's mist in terms of computation? It's edge devices. It is handhelds. It is maybe medical devices. And how else can we complete our picture? And one more, dew. Dew is droplets of fog. You can kind of get the idea here. You can get too carried away with this. We're going to focus mostly on fog computing or Internet of Things computing when we talk about cyber-physical systems here. Okay, so the thing that I've been talking about with power management, I haven't really clarified it until now. And when we're talking about buying and selling power, we're talking about something called transactive energy management. And this picture is actually abstracted from a system that we constructed in a research project. And the way to read it is that you have individual computers called DGIs here, if you can see them. They control individual power electronics devices, which then control energy resources such as wind, such as solar, energy storage, such as batteries, and then loads, which are lights and stoves and furnaces and things like that. So the way transactive energy works is you embed it into a series of houses. This is a picture on campus here of our solar village. So these are solar houses that were built by students, and they're internetworked into an electric microgrid, which can do transactive energy management. So think about one house here says, hey, I've been generating power all day, I've been storing it, I have a lot of it, who needs some? Well, how does that occur? That is a message that gets sent between the computational elements of the system. They then respond. So this is a distributed protocol. I have some need. The red one here has even more critical need. How does the system respond? Excuse me. It discharges one device and then tells another device or another house, this is, okay, you can start drawing power. I migrate or transfer power. If you're familiar with electric power, the notion of commanding a power system to transfer power is significant, because what it does, it allows you to now have pinpoint control of the underlying power system, much the way that we do in computer operating systems. We can control process scheduling. We're now controlling physical power scheduling. To construct such a system, you actually have to dynamically manage it. So you start up and one device thinks, hey, I'm all by myself. I'm all by myself. Wait a minute. Let's get together and form a group. And these groups can form dynamically. Likewise with the computational elements. Hey, I'm by myself. I'm by myself. Oh, wait. We can form a group, and we're managing the power systems as a group. So this is how neighborhoods are dynamically formed in such a system. So this is an example of a cyber-physical system that I really want to continue to use as a running example here. So hopefully this is beginning to make some sense. I now want to turn towards security, more specifically, and threats. So let's do a taxonomy here of threats. Physical threats. What's a physical threat? It's things like that. You know, I think we know how to deal with physical threats, at least to the limit that we can. Things blowing up, things being attacked from a perimeter. We're not talking about physical threats here. All right, what's cyber? Well, typically when someone says we have a cyber threat, what's the first thing that comes to your mind? And it's this: exfiltration of data, releasing passwords, releasing account numbers. Okay, we're not really talking about that either. What we're talking about are these last two: cyber-enabled physical. And there was one of the first ones of those. This happened a few years ago with the attack on Ukraine, which then got into their control systems and opened a bunch of circuits and actually caused a nationwide power failure. That is cyber attacking the physical. And just for completeness now, what's that? What could that possibly mean? Why am I showing a chemical plant? Because think about it this way. I can steal stuff just by watching the power fluctuations or the amount of material that comes into a plant or the amount of product that leaves a plant. So now the physical presence causes this data exfiltration, and now I've turned physical observations into a cyber attack on privacy. It's clever, doesn't it? A lot of different variables. Okay, obviously we'll solve it all with firewalls, clearly. Encryption, everything will be great. Yeah, right? No. I don't know how many of you people recognize this character. He's from the 50s. What, you worry? So what could go wrong with all this? Well, let's take another look at this. This is attributed to a PhD student of mine by the name of Jerry Hauser, who came up with this idea. This is actually a castle in, I think it's Lithuania. The drawing is, but think about castle security. If you've been in any place in Europe or any place around the world where you see a medieval type castle, they kind of look like this, and you're worried about the threats. So how do you guard your castle? Well, you build a good wall. See that wall around there? That'll keep the bad people out. No problem. But wait, what's that? Well, if you go inside that, that's a castle with thicker walls. Well, why do you need that? Well, it's because these outer walls might be breached by an attacker. Oh, so your firewall or your wall there wasn't so great. But that's okay. You can stay inside the inner castle, and those walls are even thicker. Well, it's not very big, and after a while, you know, that water outside looks pretty darn good, and you start getting pretty thirsty. So what does the attacker do? They just poison your well. Sigh. The meaning behind showing this is that our notion of security and security domains and high and low security is pretty primitive. It's about as advanced as a 12th century technology for building a castle. Walls only do so much. Our firewalls in cyber only do so much. We have to go farther beyond. Now, let me take this out of the 12th century and go back into something more modern. This is from a National Academy report a few years ago, and it talks about a SCADA system. You can see what the acronym spells out down here towards the bottom of the slide. And the National Academy views a SCADA system or a control system, like was used in Ukraine, the following way. We've got a control center, and we have information that is passed around the control center. Those are the orange arrows, up or down. And so the control center sends data to or receives data from control units who then either read data from sensors, such as a power flow sensor, or they open a switch, which is an actuator. Then we have a different entity down at the bottom of the screen, which is the business office, the people that do billing. And then we also have partners, because if you're familiar with the utility industry, you tend to buy and sell power from partners, independent service operators. And so we have communication with them. And then we have communication to the business center, and we have communication from the business center to the SCADA system. Now, that's a generic picture of here. There is a problem with this picture, the way it's drawn, that has been known for quite a number of years. There's exactly one of these arrows in here that should not occur. I'll give you a little quiz here. Which arrow should not occur? And the hint is it's the connection between the SCADA system, the actual process control system, and the business office. Should we be able to read from the SCADA system to the business office? Well, you might think, yeah, is that a privacy or confidentiality issue about what's happening in the SCADA system? Maybe. What about being able to write from the business office to the SCADA system? That's the bad one. And think about why. What's the business office connected to? It's connected to the outside world. People plug their own USB drives into it. They go search cat videos. Who knows what's happening? Anything that infects the business office then can infect the SCADA system. And that's exactly how attacks come in such an environment. So this is well understood by the Department of Energy. It's one of the original best practices for designing such a system. Don't allow writing from the business office into the actual process control system. What's really nice is, I'm an academic, and when you can relate something to a textbook, it's even nicer. This is an example of something called the Diva Model. And Diva was invented in 1975 and talked about integrity levels. And it talks about higher integrity to lower integrity. And the way the Diva Model works is that if you access something that's of a lower integrity level from a higher integrity level, your integrity level drops. To put more into popular context, think about this. Everybody's familiar with this ridiculous program. So if you watch it, your IQ drops. That's the joke. So don't do that. Don't look for something of less integrity than you are. Let's bring that back to our system, our SCADA system here. So how does the Diva Model tell us? We already know that we can't write from into the SCADA system, so it tells us that the business office here is of lower integrity. Well, that also tells us then that we really need to talk about security, and then we'll come back to integrity in just a second. So security. This is the classic model that we deal with in terms of security. And it's called Bell-LaPadula after the original authors. It's a military model. And we've all heard from the movies, top secret, secret, confidential. Well, it's predicated on the following. Don't read up. In other words, unclassified should not be able to read top secret. The dual of that is from top secret should not be able to write down to the unclassified level. Makes sense, right? Well, let's run forward with this. So it's a military model. So let's say we have a military commander at the secret level, and they need to communicate to their troops. How do they do that? Because remember, you can't write down. You can't write from confidential or higher secrecy to lower secrecy. What do? They downgrade their security. They're trusted. Trust is actually one of the bane of existence of security. But let's keep this model, this strict model in mind for just a second. Remember, don't read up, don't write down. Now let's apply this back to our system. So here, the Bella Padula view of the system, and we still have as well, you can't write from the business office down into the SCADA system, which means that the business office is higher security than the SCADA system, than the control system. Likewise, the system control center is higher security than the terminal units, which is higher security than the stuff that's outside. I guess that makes sense. But I can read. And then the question is, what do I do with my partners? Are they higher security than me or lower security than me? Well, if they're higher security, I can write to them, but I can't read from them. If they're lower security, I can't write to them, but I can read from them. So we're all one big happy family. The result of all this is that of all the security analysis we do, the best we can do out of a modern system is that we have two security domains. One is the entire physical system. The other is the business office. A little frustrating. Let's apply that to this. Oh my. It's hopeless. There's no way within a peer-to-peer architecture to apply a strict hierarchical security model. So what do we do? How do we get on top of this? We need to go back to that earlier picture about a person's home is their castle. And let's see what that looks like. So this is my artwork as opposed to the professional artist. I apologize for that. It's really the same picture. And let's take a look at, you're sitting inside of a house. Let's say house number C there on the right. How do you view the world? You can see that power is flowing, but you can't really explain where it comes from. To you, power flow is non-deducible. Likewise, you're over here in house A, you see power flowing, but it's non-deducible whether it's house B or house C or what's happening. Things change, but you really have no clue as to why they change. But governance here can see all the aspects of the houses and all the power flow coming in and out. So the power flow becomes deducible to them. So now we have the same sort of environment that we talked about earlier with the neighborhood. Let's look at this a little more theoretically. And I realize it's kind of hard to visualize power flow, so I'm going to flip us around here to water flow. This is a system common in the United States. It's a gravity feed water system. The tower at the left there, water is pumped up into it, and then it drains out during the day for people to use. Well, let's look at the information that's present in this physical entity, in this water flow. And I sit here in house C, and I'm trying to figure out what's going on. Well, a couple of things can happen. One is the water company can start messing with the water supply. They may shut a valve down, which means your water pressure drops. Or your neighbor turns on their sprinkler. In either case, your water pressure drops. The question is, how do we develop a security model that describes this? Well, the very basic one, and it's called non-interference by Gauguin and Mesker from the 80s. And it says that high-level events don't interfere with low-level outputs. Let's interpret that. So the utility is in the high level, the houses are in the low level, and the utility does a command. Let's try to apply this strict non-interference model to this simple physical system. So if the utility changes the water flow at all, I'm going to notice it down at house number C. But wait, that's not possible. If the system is non-interference secure, I can't do anything that is observable by house C, which means I can't issue commands to the water system. This is a ridiculous cyber-physical system. It's not possible. It's a terrible model. Yet this is the most common security model there is out there. In fact, if you look at a lot of cyber-physical systems, people talk about non-interference as a potential model, but it's absurd because you can't do anything. So let's see what else is out there. About 1990, Colin O'Halloran came up with the following model. Non-inference. I didn't pick up these terms, but interference and inference are different. And the idea is if you take a trace of the system and remove high-level events, you still get a valid trace. Let's see how that works in our water system. So again, I got the command, I got the observer. And I see over at the observer there that the water pressure dropped either from the utility or it dropped from the neighbor turning on their faucet. Huh, I don't know. I really don't know why that change occurred. All of a sudden, I see that the information has changed in my water, but I don't know its source. Now I'm beginning to get a way of securing the system operation from, let's say, house number C here, a potential outsider. Well, let's carry this a little bit farther. Non-deducibility, I used that term earlier without defining it. And it says a low-level observation is compatible with anything. So let's now go back, same picture, but now houses A, B, and C and the utility are all different security domains. C sits there and wonders what's going on. The utility changes the water flow. Okay. Or the house B changes the water flow. The water flow changing, both those events are indistinguishable to me. I'm still left in doubt. Same thing if house A does it. This is really cool because now all of a sudden I can completely block information flow of what's happening to house C, but still allows house C to see that something is happening. Think about how valuable that would be back with that earlier graph I had about the appliances in the morning inside the house. If you could see that something was happening but had no idea what it was, you'd have some pretty good security. This is the kind of fundamental way that we relate now information flow to a physical entity in a cyber-physical system. So back to our picture here, the overlapping security domains. We have non-deducibility, and governance now can deduce, but it can only deduce so much. It can only deduce what's happening in the boundaries of the house, but it still maintains the privacy and confidentiality of what's happening within the house. So, is non-deducibility good? Well, yeah, it keeps stuff from leaking from the secure domain out to the unsecure domain. But there's a flip side to this that's really intriguing. It's bad in the sense that if the outside domain can fool the inside domain into not understanding what's happening, in other words, a lack of situational awareness, then that's really bad because an attacker can now destroy the integrity of your system and you won't know it. So non-deducibility is a bidirectional model. This has been known since the 80s. This is not brand new stuff, but how it applies to cyber-physical systems is really fascinating. So the challenge is to simultaneously make sure the bad guys don't see confidential information, but make sure the good guys, the defenders, can tell what's going on in a cyber-physical system with the same model. Well, same PhD student that drew the artwork earlier came up with this. You knew there had to be equations. And this is a modal logic expression called multiple security domain non-deducibility. And the way to read it, if you look at that formula down there, is it defines over a series of worlds, which are essentially collections of states of the system. It's always true that for two disjoint states, such as water flow is on, water flow is off, if I can maintain that I don't have what's called a valuation function from a particular domain for either one of those states, I have a non-deducibly secure system. So from the point of view of our houses, inside the house, I do not have a valuation of whether or not a particular faucet is on or is off. We can use this to actually analyze a system and quantify its security. And the example we first did was Stuxnet. You may remember Stuxnet from the news. It was an attack on a nuclear processing facility in the country of Iran, and it worked as follows. If you look at the left-hand part of the picture with security domain 0 here, it was a series of centrifuges processing fuel. The programmable logical controller here was infected with a virus called Stuxnet. And so what happened is that the PLC would read from the actual physical system, and these metrics over here on the left I'll explain in a minute, but I means information flow. Stuxnet would receive that, it would modify the information flow, and then send it up to the PLC. The PLC had no reason to disbelieve that it wasn't seeing the actual readings from the centrifuges, but Stuxnet had manipulated them such that they look realistic. It then fires them on up the line and to the operator and says, hey, everything looks good, everything looks fine. What Stuxnet did is it made in security domain 4 there the system non-deducibly secure to the operator. I'm going to repeat that. Stuxnet made the system non-deducibly secure to the operator, and that's a bad thing. So it depends which direction the information is flowing and who is the defender and who's the attacker, whether security is even good or bad. Now the question is, what does the human do? What does the operator do in such a situation? The operator becomes suspicious of this and says, I wonder if this is really true. I'm getting information flow, but do I believe it? That's the not belief and the not trust that's there on the right. So the operator gets up out of their chair, goes downstairs, takes a look at the centrifuge, takes a reading, compares it with the trace of the readings, and realizes those don't match. What the system is telling me and what the physical system is doing are very different. So by doing that, I add a valuation function in that allows me to break the non-deducibility of the system. So by breaking security, I make the system more resilient to attack. I realize it's a bit of a challenge to wrap your head around that particular thing, but again, it depends upon the direction of information flow that you're trying to secure. So that's all well and good in the abstract, and Stuxnet was one attack. Does this scale to anything? Well, it does. And so we worked with our friends in Singapore a few years ago, and they have a scale model. This thing is the size of an entire factory floor, a scale model of the Singaporean water treatment system. So it's a fascinating project to work on because you could destroy things without doing any real harm. So there's another picture of the physical system. It's located at the Singapore University of Technology and Design. It's got 6 processors in it, and sensors and actuators. And so we applied this MSD model to that. I'm going to pick out just one part of this really complicated diagram. But as you can see, water comes in from the left, it moves off to the right, it goes through some pumps, it comes back around, it moves through some filters, it's some ultraviolet filters, it has a backflush capability, and then potable water comes out the other end. So it's a water treatment system of raw water into drinkable water, which is fundamentally what it's doing. I'm going to zero in on the upper left-hand corner of it in just the first stage of this process. Raw water comes in there, a bunch of PLCs, and so here's process 1. I've got a tank, raw water comes in, it's got a pump that pumps it out, it's got a valve that controls whether I'm accepting more water or not, it's got flow sensors, which can tell me what's actually happening in the system. And the programmable logic controller then has a fairly simple point at this point of view. It fills the tank until the tank's full, and when the tank's full, it stops filling the tank. Pretty simple idea. But each one of these in the MSD model is its own security domain, and they're interacting with each other, as is the PLC. So the PLC, if it's infected, sees the following. The level indicator here is a float in the tank, which is measuring the amount of water in it. And so it's getting information from the tank to the level indicator, which is correct, like it was in the Stuxnet. It tells the virus what's happening. The virus lies. The virus tells the PLC something different is happening, and then that goes to the operator. The effect of this, and we did this actually, we have a video of it, is we overflowed the tank by fooling this thing, and the pump just kept pumping, and the water went all over the floor. They put a dam around the tank after we started doing that. So how do we analyze this? This is the mathematical analysis behind this, and I'll be happy to discuss this independently if someone wants to work through it. But the key is that middle expression. We lose a valuation function from the security domain of the operator of what's actually happening down in the system. That's bad. How do we break it? Well, this is the part that becomes more difficult. How do you fix this? By breaking the inherent non-deducibility security. You have to add more information. And the information that we added in is a very simple relationship. It's a flow invariant. Invariant is something that's always true. No matter what the configurations are, it's always true. In this case, it's just the water view of the power system Kirchhoff's laws. Water inflow minus water outflow is constant. The water comes in, it has to leave. It stays in the tank. If too much water gets in the tank, then it's going to overflow. So there's a balance that has to be maintained. So let's redraw the attack here. Same sort of flow, same sort of lying, same sort of bad report to the operator, but now the operator has an additional source of information, which is this invariant. And by looking at the flow indicator on the left and the flow indicator on the right, can make the deduction that what I'm hearing from the PLC and what should be happening from the system are not the same. I have a problem. That's the mathematical analysis as well. And if you look at the bottom, the key part is there's one of the not exists is changed into an exists. And now I have a valuation function on the system, which allows me to break the non-deducibility security and preserve the integrity. We implemented this as part of the SUTD project. There's a flag, a monitor here. In fact, this is a really excellent thing. They run red teaming exercises every year when they invite teams in to come and try to break this system with these defenses in place. To my knowledge, they've never gotten past the first level of defenses or second level of defenses. These are still waiting for them, but we know how to attack the system, so we can break through that and finally get to the final point where, no, you actually can't get past us. These are just some various snapshots of some of the details. I'm not going to go these in any detail at all, other than just to say, what am I going to do with this? So this is another typical result. And it's the same thing we did with the two previous pictures I just showed, is what can you do with this? If I look at the number of information flow paths that are in any system, this is another result from a power system as opposed to a water system, I get a count here of the amount of information flow paths there are. I can then use MSDND analysis to tell you the MSDND secure paths that are found, which tells you the number of vulnerable paths that are on the system. In this case, there are 89. I can break them using the invariants, so I can break 73 paths, and with just 24 invariants left in the system, what have I done? I've established a measure of resiliency for the system, for the security of the system, which is really hard to do. But I've done it in terms of this common cyber-physical information flow. I've given the fact that it's this vulnerable. I've mitigated those vulnerabilities, but if you scrap those two numbers, I've still got 16 vulnerable paths. But I've improved the resiliency of the system by at least that amount. Now the question is, what do you do with that information? You can sit there and say, okay, well, my system still has the resiliency. Then you have to go through the analysis. How likely are these? Or what you do is you redesign the system to get rid of those remaining secure paths. Because every time you have one of these secure paths, you have the potential for an attack on your system. So again, what do you do with this information? Well, we've been working on this for a while. The MSDND work came about 8 years ago. We've been working on power systems for about 22 years. And we then decided, okay, what do we do next? We've done this analysis on a lot of different systems. It's a manual analysis. So we measure the system security resilience using this uniform information flow model. It allows you to quantify the vulnerability of the system. We improve the design. How do you improve the design? You mitigate the MSDND paths. Then, how do you do that? You use engineered knowledge. You use the knowledge of water flow must look like this, power flow must look like this, system stability must look like this, traffic flow must look like flow invariance, must look like maximum flow. And this provides an active defense against both these kind of attacks that I talked about, the cyber-enabled physical, and you can make a very easy argument now that it protects against physically enabled cyber because of the dual nature of information flow. The conclusion we've come up with, though, after 22 years in the field and 8 years using this technique, it's hard. It can take a couple of years to actually break down the system. Not terribly practical for an industrial application. We recognize this. So we're currently funded by the U.S. National Science Foundation to do the following. Let's automate this. Let's abstract the notion of the invariant into this owl icon. In U.S. culture, there's something called the wise old owl. I know it doesn't extend around the world. But the owl can spy on parts of the system, but it can only spy on parts of the system. That's the spyglass. And the spyglass gives you the valuation function. So let's automatically construct these security domains that the owls can look at optimally. Then let's, instead of struggling with each single infrastructure, what is an invariant in water? What is an invariant in power? What is an invariant in aviation and chemical plants? Let's abstract this into something called a port Hamiltonian system. These have been around for a while, again, trying to do the same thing, trying to provide abstractions. We have a slightly different take on it, trying to abstract the control systems along with the physical systems such that once you solve it for this abstract nature, you can go back to the actual physical system and don't have to rethink it every single time. Likewise, state estimation. How do I know those sensors that I'm reading from the water system are actually giving me the correct information? That's one problem. The other one is that real sensor readings are rarely precise. There is some noise in it. So how do we distinguish between noise and between an attacker hiding in the noise? The last one is, instead of asking the engineers to come up with all these invariants, let's monitor the behavior of the system. Let's use data science now, data mining, to learn the behavior of the system and learn what's known as ground truth, how the system should really behave. So this is what we're working on right now. Some initial discoveries are somewhat frustrating. And they go as follows. In the top picture here is we have our same water system. We ran the design-centric defenses against this, the ones that I mentioned earlier about the invariants. And then our data science expert did a huge amount of data analysis of the same system, and we came and compared the two at the end, and they diverged from each other. So there were two reasons for that. One is what the engineers thought the system was doing wasn't actually what the system was doing. Due to various implementation constraints, the data-centric learned the system perfectly. Unfortunately, it didn't learn that system. It learned another system. Because if you think about it, no matter how much data you collect, you're not going to be able to exercise every possible operational mode of the system. So you're going to learn a subset of it. And as soon as the system behaves as it's intended to do, but not the way that you've measured it, you're going to flag errors. Now you can see exactly what's going to happen next is an attacker, a wily attacker, will poison your data. Data poisoning is a real term, and cause you to learn the wrong rules. So we have to have a coupling here between the design-centric and the data-centric aspects. The bottom graph here is another problem in which an attacker is attempting to steal power, and they do so by hiding in the noise. While at the instantaneous, you can't detect it, but over time, you can see the amount of power stolen continues to increase. So there's a lot of work that still continues to be done on this area. All right, so I'm nearing the end of my presentation. I just wanted to wrap up a little bit. On the left, I would say that most of our security work these days still looks like the 12th century. It's a castle with walls. It's an Maginot Line from World War II. Fixed fortifications are a good start, but it doesn't address cyber-physical aspects. It doesn't address insider attacks. The modern environment is overlapping security domains and the flow between the security domains. And this is, I think, my major takeaway here, is that we need to rethink how we draw security and secure interactions in a modern cyber-physical system. And I'm pausing for a second because I'm going to transition to a couple more slides. We've all seen this trolley problem. The setup, if you haven't seen it before, is there's a runaway trolley. And there are 5 people stuck on the tracks on one track. There's 1 person stuck on the track on the other track. And you're standing there with a switch. What do? Now, of course, it's a philosophical argument. There's no correct answer to this. You have three options. One is you can leave the switch to go straight ahead and kill 5 people. You can throw the switch, kill 1 person. And the third option is to walk away and do nothing. It's not your fault. And you're wondering, why did I put this in here? Well, think about the modern cyber-physical system aspect of this. This is a self-driving car. That trolley is a runaway car. You have to make a decision. What do you do? Except it's not you as a human. It's the computer system that you build. So it's really fascinating as we go down this path of cyber-physical systems, embedding humanity into it, embedding society into it. How do we drive ethical thought into a cyber-physical system? So if we were live, we would have a really nice interaction at this point. I'll just give you a very quick summary of it. I did a sabbatical in Norway, and I gave the same talk. And usually when I give this talk, people kind of nod along. Okay, I could see it. The focus was on privacy. And I finished the talk to a completely silent audience. I'm thinking, what did I do wrong? Well, I later learned from a German colleague that, oh, well, the perception of privacy in Norway is very different than the US. And it dawned on me at that point that this whole notion of privacy, security, confidentiality is very cultural. Something to think about. Will people use this idea? Well, if you can improve your resilience against cyber threats, yeah, probably it seems reasonable, but there's a long path to get here. And I think we do not need to underestimate the difficulty in trying to secure these systems. And finally, I see, there's a question that came from Mr. Sharm. How is fog different from cloud? Yeah, fog is something that is much more invasive, much more localized. And then the ethical issues of spying on your neighbor. Interesting. So a lot of fascinating thought here. This is why I love doing these visits. So I'll give one more plug here for the Computer Society. I've done a number of these visits. I've been around the world, met a lot of great people. I love the fact that local seminars brings people out to get together. And what the Computer Society provides, in addition to this outreach, is ensuring quality of the discipline. This is kind of the Wild West out there sometimes. People talk about data science, cybersecurity certifications. The Computer Society supports accreditation of programs, peer review of programs, peer review of publications to ensure quality, and then provides standards. There's a lot of work for standards in this. So anyway, I thank you for your time. It's been enjoyable to talk, and I believe we have some time for questions.
There have actually been quite a few questions that have come through. One of the questions that's out there is cyber physical system a secure IoT?
We'd like to make it so. In fact, if I were going to write a proposal that I wrote 15 years ago, but write it now, I would entitle it fog computing and secure fog computing. And because of the issues that I talked about today, the notion that we have individual subdomains of a cyber-physical system that must interact with each other in almost completely unpredictable ways. Think about a platoon of vehicles. Platoon is essentially a grouping of cars going down the highway. And each car is obviously its own security domain, but they must interact with each other. How do you secure that Internet of Things environment, which is really running into fog? Because the cars have to interact with each other, and don't allow miscreants to come in and fool your valuation function of the other cars. Because if you do that, let's say the lead car, you're watching it, and all of a sudden it fools you into thinking that it's going, but it's actually stopped. You're going to run into it. You're going to have a chain reaction. But there's no one oversight that can monitor this. So we really have to work hard to understand how, from a peer-to-peer level, from the Internet of Things level, we can manage this information flow and ensure that we always have some sort of solid valuation function of what's happening. Hope that answered your question. Thanks.
We have another. It's interesting. Your approach seems like an abstraction of the Purdue model on the OT world and integration with the IT world in the context of applying security on the complex environment that is a factory with the challenge on trying to bring components that allow us to track the information flow and prevent threats and information breaches. I guess this person is looking to see if that's what your thinking on this is.
There's a lot of common approaches out there, and I really, inspired every time I hear about another one trying to use multiple observers. Now, as soon as I say that, you begin to realize that when you start to turn securing a system into the integration of multiple sorts of information, you're beginning to talk about aspects that look like fault tolerance. Triple modular redundancy has been around for a really long time. For those of you unfamiliar with the concept, the Apollo command module from the moon missions used 3 separate computers, all computing exactly the same thing, and it would vote on the results. Well, that's tolerant of one failure, isn't it? One of the computers can fail, and you're still going to get the right answers. 2 computers fail, you're sunk. And so you do a calculation along those lines. This notion of synthesizing information with multiple observers, multiple different devices, is really the same idea. The key here is to understand that information is not just the data that's being transferred, data in transit, it's not the data at rest, but it's also the information inherently present in the physical system and the physical relationships that provide you a ground truth to be able to secure the system. In that aspect, it's probably easier to secure a cyber-physical system than it is to secure an abstraction like the internet.
I think another question we have is, do entities know where they are in the topology? So A observes flow, disturbance, and knows from the utility?
In the water system, it's pretty simple. It's a fixed topology, and the system cannot reconfigure itself. Go to the other extreme, such as the ADS-B airspace management system with aircraft flying around 200 miles an hour, and they move constantly. So you're talking about mobile ad hoc networks in vehicles, you're talking about VONets. And so how much specific information do they need to know? Do they need to know their actual GPS position, or is it enough to know the relative position? I don't have a super solid answer to that right now. We're working on that at this point. It's turning out you can do a lot with just knowing relative positions and relative relationships. Think about a car surrounded by other cars. I have to know who's ahead of me, who's behind me, who's in my right quarter, my left quarter, if I'm doing any maneuvers. Do I need to know who's 3 miles down the road? No, probably not. So there's a continuum here.
Thanks. This next person is asking if it's possible for us to show the different types of information flow models slide again.
It is possible. Let me see if I can do this quickly. I'm getting back there. Almost. There. Is this the one that you were after? And I guess what's the follow-on question? Well, I'll just run through them again. So these are 3 principal models. The non-interference, again, is what we're really, really familiar with. It's like the crypto model. Don't let any information or don't let anything that's happening in the secure domain appear at the outside domain. And that's ideal. It's just not feasible in a cyber-physical system because you can't control anything. So the non-inference and the non-deducibility relax that a bit. They allow you to see that something is happening, but the goal is to leave you permanently confused about what you're seeing. If you want a historical perspective on that, think about D-Day, Operation Overlord, its anniversary coming up, where the British built a plywood army across the English Channel to confuse the Germans about where the invasion was actually going to happen. That's information, it borders on deception. And deception against you is a bad thing. Deception from you against the attacker is a good thing, that dual model again. I hope I got to the right slide there. Other thoughts? Gary, do we have other questions?
Yes, sorry. I was on mute. I didn't notice that. The next question is, how does one detect a physically enabled cyber?
Detect. Yeah, that's a really difficult problem. Let's set up a particular physically enabled cyber scenario to talk about. So you're sitting outside of a factory, and they're making plastic water meters. I worked for a company that did that at one time back in a previous life. So raw material comes in, which is plastic shavings, and then meters go out. And by looking at the amount of plastic coming in and the amount of meters that are going out, what can I observe? Just that physical observation has told me the productivity of that plant. Now, can I detect that that observer actually saw that? No. I can detect, but I can tell you from an MSD&D analysis that that potential information path is there. Now, if I go back to the formal model that I talked about, how do I ensure that that information path does not exist? How do I make this observation multiple security domain non-deducible? I create fake stuff. So the water meters, you have fake water meters coming out. Some of them are made out of cardboard, some are made out of plastic. I mean, it's an absurd example. But what you're trying to do is you're trying to break the valuation function that an observer anywhere could use. But can you actually observe that can you detect that has happened? There are some proofs that show that that's actually not possible.
Okay, great. This person's asking about something you brought up earlier. They ask, who is the PI in the NSF award you referenced?
That's me. There's an echo there. It was from 2018. It's the CPS Medium program, and if I can remember the exact title at this point, I would tell you. But anyway, the PI is McMillan, 2018 award of the NSF CPS. You can see the abstract there. Don't hesitate to write me if you want to interact directly.
Okay, the next question is, in addition to restricting flows in certain directions, what else can you do to protect a CPS? That's an interesting question. We've got ourselves so deeply into the notion of protecting the information contained within the CPS. You know, the starting point, I'm just kind of pontificating at this point. Firewalls are a good starting point. I know I'm dismissing firewalls, but firewalls are going to catch a whole lot of stuff. People trying to come into the system, scripts coming at you. I think one of our corporate partners had some quote about several million attacks a day coming at them. And firewalls defeat a lot of that. Encryption of control signals is important as well, because again, it breaks the notion of the valuation function. But when you get really inside of it, the problem you're trying to address was likened to me in the following way. Suppose you're defending a castle, back to that, and you have somebody that's gotten inside a Trojan horse, and now you see somebody coming at you that you don't recognize. Are they a good person or are they a bad person? Somehow we have to be able to figure out the difference. And that, I think, is the crux of the matter. So this is not just a prescription talk to say this is the way to do it, but it's to really phrase, I think, that problem in your mind, because we're just scratching the surface of this. I know that's kind of a non-answer, but I turned it around in the sense that that's the fundamental problem. Okay, great. The next question is, how feasible is realizing autonomy in securing CPs?
How feasible is realizing autonomy? We were part of a National Science Foundation, again, sponsored project called an Engineering Research Center, which is a 10-year, literally 10-year project. And so it has heavy industrial partnership. and it was with the electric utility industry. The electric utility industry has been around for over 100 years, and they've done things in a very centralized, controlled way. And we came in and we started to talk about this Internet of Things model. And the year we're talking about here is 2006 to about 2008. We're proposing this. And even after 10 years of working together with the utilities, with electric power engineers, the concept that you don't need an overlord was still very uncomfortable to people. You know, let's look at modern VANET architectures, where virtually every paper that you see requires that you have some sort of roadside unit. And the roadside units then go back to some sort of centralized controller, and the roadside units are monitoring every car that goes by. So we have a centralized overlord. But if you start to think about the scale of that, think about millions of cars on the road. How am I going to maintain all this information? Is it even feasible? You begin to realize that probably taking an example from the physical world of how things really operate may be the way to go. You get into a car, you drive the car. Do you need to have centralized information about anything? About the only thing you need to do in driving a car is to stay between your lanes, don't run over the car in front of you, don't drive too slowly, and just be aware of your local neighborhood. Huh, that's interesting, because that system works only on autonomous, localized information. So maybe we could take a look that way. It's a thought that maybe it is feasible. Thanks.
So the next question is, what is the application for IT industry as real life, and what are the current workings regarding this at your university now?
So I mentioned at the outset, we are a STEM engineering-focused university. Some of the specific projects that we're working on with our engineering colleagues, obviously power. We've been talking about electric power, aviation management, chemical engineering management, because you think about a chemical plant with its sensors being corrupted will explode. And refineries have actually exploded because of this very issue, not because of cyber attacks, but because of just loss of the ability to do valuations. The bridge between classical IT and this, that's a little harder to see. And what is the difference between, let's say, classical IT, such as securing a database or, I don't know, a payroll system, and the cyber-physical system? Are those really different types of models? And again, I think that the cyber-physical system work is actually easier because you do have this ground truth. Now let's think about a banking system. Do you have ground truth in a banking system? Well, let's see. Yeah, I guess you do actually have invariance. You have the deposits and the withdrawals should really balance with the bank balance. Well, that seems reasonable. Securing Pokemon Go, that's an old example. That's a little more difficult to come up with. And then we can get into things like blockchain. I haven't mentioned blockchain at all. Blockchain is used in transactive energy management. Blockchain for Bitcoin makes sense because it is a way of security inherently within a completely closed system that the operations from Bitcoin are valid and auditable. But as soon as you take it out of the Bitcoin world and you try and use blockchain to secure a cyber-physical system, you run into all sorts of problems because all the validity checks that you can do are off-chain. So now you have to go back to ground truth. So I hope I kind of addressed your question there, but I'm almost thinking that the general IT problem is harder.
Thanks. This next person asks, they say that they assume a telecom system is cyber-physical. Is there anything in the 5G standard that helps the problem, this issue?
I'm going to have to just say uncle on that one. I haven't really thought about it. It's a great question. Thanks.
The next person asks, if data integrity is the key to a successful cybersecurity model, would blockchain implementation be beneficial? And then also maintaining the integrity of each transaction would be achieved this way.
Yeah, and I think that's really the key. If you're going to apply blockchain to such a system, you have to be able to secure or show the integrity of the off-chain computations. In my electric power management example, the blockchain can record the requests that were done for the energy management transactions, but it has no way of validating that the transactions actually occurred. For that, you need some sort of physical or cyber-physical attestation to augment the blockchain. I think that's really, really important to keep that in mind. The blockchain secures the request for decisions, but it doesn't actually allow you to ensure that they occurred. And that's kind of a warning. Thanks.
Okay. The next person says, I work for a smart meter company. I know that a smart meter can deduce loads by looking at signatures. I'm not aware of methods to deduce loads outside of the home. How is that done?
So the specific example that I showed you was done using hidden Markov models. We trained the system on appliance behavior. And then because of those changes, you're able to coalesce which specific types of signatures map to which specific types of devices. That sounds really wonderful in practice, and it works well in the lab, but it's not terribly scalable because of the complexity of doing that. Still, that trace actually came from another group, not from our group. So there's a feasibility with enough computation power to be able to do that. But again, that was a hidden Markov model technique that I showed you.
This one seems like an interesting question. It says people are fallible. Designs and their implementation are fallible. Should we belt the suspenders?
I think maybe that's what we're doing here. Think about you design the system, and we're working with a company, which I'll for obvious reasons, leave nameless, where they have designs and they have done a lot of red teaming exercises. Red teaming, again, is the concept where you pretend you invite the attackers in to try to break your system. But when we came in with this information flow analysis, it began to realize that this allows you to look at it in a completely different way, because you're melding the data flow with the physical flow. And you're looking at ways that an attacker can disrupt that combination. And so in a way, belting the suspenders, I like that analogy. That's really good, because the more things that you can add in, the more resilience you build in. Now, if you really want to get into a philosophical argument, of course, as soon as you begin to add more cyber components into a system, you begin to lower its resilience. That seems backwards, but the amount of damage that a cyber system can cause to a physical system is truly impressive if it really wants to be malicious.
Great. The next person asks, how do you define CPS and IoT concepts, and do you consider them as distinct concepts or the same?
That is a philosophical argument. What is the difference between an embedded system, an IoT system, a fog system, and a cyber-physical system? Marketing, maybe? Because think about the commonalities of all those different components. We'll just pick an IoT. And so it's got some sort of thing, that's what the T is, an Internet of Things. You've got interactions between the things, Internet of, that's a connection as well. What is the IoT thing doing? Well, maybe that's a cyber-physical system, but the cyber has to be doing something as well. With fog, how does that relate? Well, that's the intelligence telling the system what to do, but that's the cyber portion, which is also the Internet of Things. I might just say what makes you happy, because it's really kind of all the same concepts, but even embedded systems. The CPS community grew out of the embedded systems and real-time systems world. The only difference might be that CPS are somewhat more distributed, or they have different scales, but in reality, I think it's these principal components you have to keep in mind, whatever you call it.
Great. The next person asks, can there be more security applied on hardware devices when talking about cyber physical threats?
Yeah, there's a dual aspect to that. Just kind of pick them apart. One is the question, is the hardware device that you have the hardware device you think you have? And one way of measuring that is to be able to measure the radio emanations that come out of the device. So you know what the device was supposed to do at the factory. Now you have the device in the field, and you monitor the device to see if it's actually behaving the way by its radio emanation signals or by its electric power usage. So it's one way of diagnosing the integrity of the underlying hardware. Well, let's flip it around another way. You buy a piece of hardware from a vendor, you put it in your system, and you have a certain functionality that you spec'd out. Is that all the functionality that's in there? Because if you ever tried to pick apart a very dense circuit, you can hide lots of stuff in there. So how do you ensure that there isn't malware embedded in the hardware device? And that's a different problem. Maybe the radio emanations can help there, or maybe you need a different form of attestation to say that, again, I feed it this input, and it should only produce this output, and its security domain should be constructed that it can't do anything else. Or more succinctly, does it do what it's supposed to do, and does it not do what it's not supposed to do?
This next person notes that the water tank examples also illustrated in hybrid specifications with the purpose to verify the behavior of the system. How can your model be integrated with hybrid specifications?
I mean, like embedded hybrid systems, I'm assuming that's where the question is going. So the challenge of embedded hybrid systems, of course, is on a uniform model to be able to express the control system. My control system, the water example, is really simple, and the physics of the underlying system. That's been a challenge in embedded hybrid systems for quite some time, and again, it's the space complex, or the complexity of the combined model that becomes a challenge. This was one of the reasons for our forays into Port Hamiltonian systems. Without getting too deeply into it, Port Hamiltonian systems is an abstraction that translates potential and flow, and most systems actually have these same concepts. The water was a particularly blatant example of that, because the potential is the height of the water in the tank, and the flow is the movement of the water through the system. If you can abstract it enough, maybe you don't need tremendously detailed analysis, and you can try to get away from the complexity problem. But this work is still somewhat embryonic. We have been noting it for the last, probably get the time wrong, at least 15 years of people attempting to foray into this, and there are constant frustrations with attempting to do this. But if you could do this, you would really have something, and you would be able to describe the correct behavior of the overarching system without getting bogged down in its details.
This next question had jumped into my head as you were giving your presentation earlier also. Does automation increase or decrease security?
On the outset, if you're not careful, it probably decreases the resilience, and then you can tie the two of those together. Case in point, this was a much earlier project we were doing with the Department of Energy, and we had developed an abstract model of what it would take to have prevented the 2003 Northeast blackout. Call us back 17 years ago. It was a system where a highly stressed transmission system was knocked down by the failure of a very inconsequential or seemingly inconsequential link, which just initiated a cascading failure. I realize this is an oversimplification. But imagine a cyber system controlling the power distribution of such a system, and it is now malicious. Just the slight change can actually take what is a pretty reliable system and decrease its reliability significantly unless the cyber system itself has an almost perfect type of resilience to it. This same sort of model is used in aviation, where the amount of failures per year is some fantastically small number. You can look it up, 10 to the minus 99th. How you validate that, I have no idea. But that's what's actually required to keep the cyber system from lowering the resilience of it. So when you add cyber systems in, it has to add some sort of benefit. Hopefully, I at least made partial case today that by having the cyber system be smart and understand what's supposed to happen, you can not only compensate for that, but also improve the resilience of the system.
This next person asks, can we ensure logical integrity in transition from cyber to physical and back?
Logical integrity, let me think about that one. Trying to answer that. The physical system understands it's being acted on by the cyber system. The question is, can the physical system protect itself based on bad cyber commands? And there's some aspect of that. Think about a crazy cyber command in a car, a vehicle, and it's telling the vehicle to run off the road. Well, I have some protections against that. The little vibrate strips used to have some of the cars I've rented vibrate the seat if I start to run off the lane. So there could be some physical protections from the cyber system improperly sending information flow. The reverse as well is what I've been focusing on today, which is the cyber system picking up readings from the physical system. The physical system is doing the right thing, but it's the way that you can observe it that can get corrupted, and that's a breakup of the information flow. So I think they can partner with each other, but again, that's also a risk in that boundary.
Let's go ahead and make this one the last question here. I know we've got lots of questions to get to, but we are quite a bit over. This person asks, can physics for each particular CPS be used to detect attacks?
And I think that is just the perfect answer. Physics of the system, you can't violate Kirchhoff's laws. The cyber system can try to violate Kirchhoff's laws, but the physics provide a ground truth. And I think that's the thing that if we can rely on, that's what makes the cyber physical system easier to secure than a purely abstract system. So yeah, great observation, great question.
So Dr. McMillan, I'd like to really thank you for talking to us today, giving this presentation. I have to say that I really enjoyed the fact that you used a lot of analogies, and that it helped me understand quite a bit. I felt a little bad, though, that I did know who Alfred E. Newman's age a bit. And I was interested in the cultural elements of privacy. I thought that was quite an interesting thing. So I thank you very much for presenting to us today. I'd also take a moment to thank all of the people who attended, have you. So in addition to the Distinguished Lecturer webinar series, we also offer Build Your Career webinar series that focuses on business soft skills such as communication and presentation skills, career transition, interviewing tips, among others. The next webinar will be The 4 Languages of Influence on May 14th at 11 a.m. Eastern Time by Roger Granis. That's the principal of the Granis Group. The next webinar in the Distinguished Lecturer webinar series will be on May 26th at 6 p.m. U.S. Eastern Time. Dr. San Murugesan, Director of Bright Professional Services and Adjunct Professor in the School of Computing and Mathematics at Western Sydney University in Australia, will present on IT and the fight against COVID-19. This webinar is going to be co-hosted by the Special Technical Community IT and Practice. And the last one on May 28th at 10:30 a.m. U.S. Eastern Time we will be hosting the webinar Machine Learning for Medical Imaging Analysis Demystified, presented by Dr. Amlan Chakrabarty, professor at the University of Calcutta. The registration is now open, and we will be sending you a link for these future events, along with the slides and the recording of this webinar. So again, I'd like to thank all of you for coming, and I'd like to thank all of our members for supporting our organization. And Dr. McMillan, thank you again for your presentation. Everybody have a great day.
Bye, everyone.